Welcome to the Deep Dive. We're here to cut through the noise and get you informed fast. Today we're tackling a question that used to be pure science fiction, but now it's a real challenge for AI researchers and roboticists. Does artificial intelligence actually need a physical body to get to human-like intelligence? I mean, think about it. You've got Rosie the robot from the Jetsons, right?
Yeah.
Or Joshua in War Games, even Samantha in her. AI has been imagined with and without bodies for ages. But it's not just speculation anymore. It's a really pressing issue in AI right now. Our main source for this deep dive is a really thought-provoking piece by Star Vartan in New Atlas. It came out June 29, 2025, and it's titled, "Do AI Systems Need Bodies for True Intelligence?" So our mission today, we want to unpack the maybe surprising limits of current AI, the kind without bodies, then explore this kind of radical idea of embodied cognition, and finally look at how things like soft robotics and autonomous physical intelligence might be creating a totally different path for AI, maybe a more truly intelligent one.
Right. And we'll also try to connect these ideas, which might seem a bit abstract, to that big ultimate goal of artificial general intelligence, AGI, and maybe even what it means for how we understand intelligence itself.
Okay, let's dive in. Where are we right now? Well, despite all the amazing progress, there's a kind of quiet alarm bell ringing in the background of AI research. It seems even the most advanced systems, the ones that feel like they're right there, are hitting some kind of fundamental wall. It's puzzling. Yeah, take this new Apple study. They looked at something called large reasoning models, LRMs. These are basically like souped-up LLMs, large language models. They're designed not just to spit out an answer, but to show their thinking, their reasoning steps.
Okay. The idea being to get closer to how humans actually reason through things.
Exactly. But here's the kicker. The study found, yeah, they do okay on simpler stuff. But when the problems get really complex, they don't just sort of level off. They completely collapse.
It's collapse, not just make a state.
No, collapse. Even with plenty of computing power, they just fall apart.
Wow, that's pretty striking. So if these cutting-edge LRMs just break down when things get tough, does that sort of undermine the whole idea that just making models bigger, feeding them more data, throwing more compute at them, that's the path to real reasoning? Are we maybe barking up the wrong tree?
It definitely makes you wonder, doesn't it? The study said they failed to reason consistently or algorithmically. They're so-called reasoning traces, the steps they supposedly take. They lack internal logic. And here's something really weird. The harder the problem, the less effort the models seem to put in, almost like they just give up. The researchers basically concluded these things don't really think like us. Nick Frost, formerly at Google, now co-founder of Cohere, he put it pretty bluntly. He said, what we're building now are things that take in words and predict the next most likely word. That's very different from what you and I do.
Okay, why is that difference so crucial? How does just predicting the next word fundamentally separate these AIs from, actual human thought or reasoning?
Well, it's a huge distinction because for a long time, AI research followed this model called Gobe-Fei, good old-fashioned artificial intelligence. Gobe-Fei treated thinking as basically symbol manipulation, like computer code. The idea was you don't need a body for abstract thought.
Right, intelligence as pure logic.
Exactly. But that whole concept started to unravel when the first robots, the ones based on Joke AI, just couldn't handle the real world, messy, unpredictable situations. So then researchers in psychology, neuroscience, even philosophy, they started looking elsewhere. They looked at how animals, even plants, actually learn. And they learn through physical interaction with their environment, not just abstract ideas.
Interesting. So learning by doing, essentially.
Pretty much. And this led to the idea that maybe intelligence isn't just locked up in the brain. Maybe it's distributed through the whole organism. Think about our own gut, the enteric nervous system. It's often called the second brain, right? Uses the same kinds of cells and chemicals as our main brain. Or, even cooler, an octopus tentacle. It can sense things and react all on its own, locally, without needing constant orders from the central brain. It's like the limb has its own intelligence.
Local decision-making.
Yeah. And all this points to this really central idea, embodied cognition. The core concept is that acting, sensing, and thinking aren't separate. They're basically one process. Rolf Pfeiffer from the University of Zurich's AI lab said it really well. Brains have always developed in the context of a body that interacts with the world to survive. There is no algorithmic ether in which brains arise.
That's a really powerful quote. It shifts the whole perspective. So if intelligence is distributed and it's tied up with physical interaction, What does that mean for how we should be trying to build AI? Does it mean we have to give AI bodies to make them truly smart? Or is that just us trying to copy human evolution, which maybe isn't the only way or the most efficient way for AI?
Yeah, that's the million-dollar question, isn't
Yeah.
it? This embodied cognition view suggests that, yeah, if you want an AI to truly understand the world like we do, it probably needs a body to experience it directly.
Mm-hmm.
And if intelligence is distributed, maybe we don't just need smarter software, we need smarter bodies too. Which, and this is really fascinating, brings us right to the field of soft robotics.
Ah, soft robotics, making robots squidgy like an octopus.
Kind of. Cecilia Laschi is a big name here. She argues that smarter equals softer. She actually spent years working on rigid humanoid robots, the classic sci-fi kind. But they were incredibly hard to program for anything unpredictable. Walking on uneven ground. A nightmare.
Right, you'd have to code for every possible bump and tilt.
Exactly. So she shifted focus to soft-bodied machines, inspired by, you guessed it, the octopus. No skeleton. Limbs that seem to think for themselves. Think about how we walk. Your knee naturally bends and adjusts if you step on uneven ground, right? That compliance is mechanical. Your brain doesn't have to consciously micromanage every single adjustment.
That's the body doing some of the thinking then.
That's embodied intelligence in action. It's outsourcing some of the cognitive load to the body itself. And from an engineering standpoint, this is huge. If the body can handle some of the perception-controlled decision-making, it dramatically cuts down the computation needed in the main brain.
Yeah.
You get machines that can handle messy, unpredictable places much better. Last, you put it this way in science robotics. Motor control is not entirely managed by the computing system. Motor behavior is partially shaped mechanically by external forces acting on the body.
So the environment itself helps shape the behavior through the body.
Precisely. Behavior emerges from interaction. Intelligence is learned through that physical experience, not just loaded in as software. Okay, so to make these soft robots really work, like that octopus tentacle, roboticists are moving beyond just programming everything. They're designing materials that can sense and react intrinsically. And this leads to another really cool concept, autonomous physical intelligence, or API. Minhye at UCLA is doing amazing work here. She designs soft materials like gels and polymers that don't just react to stuff like light or heat. They actually regulate their own movement using feedback loops built right into the material itself.
Wait, built into the material? How does that work?
She calls it having more decision-making ability at the material level.
Yeah.
Back in 2018, her lab showed a gel that could kind of oscillate or move on its own in a controlled way. They've applied it to other soft materials too. The key, something called nonlinear time lag feedback.
Okay, that sounds complicated.
It is a bit, but think of it like this. Instead of a central computer telling the material exactly what to do every millisecond, the material itself has a sort of built-in memory of what it just did. This little time lag in its internal feedback lets it naturally correct and adjust its movement. It allows for controlled, rhythmic behaviors.
Like walking or breathing.
Exactly like that. Think about how your body regulates glucose levels, or how a pendulum swings back and forth naturally. There's an inherent rhythm in self-correction. It's not someone pushing the pendulum constantly. API aims to embed that kind of logic into the material.
Okay, so this decision-making at the material level, what does that look like in practice for a robot? How is it really different from a standard robot that has separate sensors, a processor, and motors?
Well, the big difference is integration. In an API system, the material itself is performing some of the sensing, the processing, and the acting, all kind of interwoven. So the material changes shape, maybe due to light hitting it. Then, based on how it deformed and its built-in properties, that time lag feedback, it effectively decides how to react next, maybe modulating how much light it lets through or changing its movement pattern. It's a continuous loop within the material, not separate steps managed by a central computer.
Right, so it's not sensor, processor, actuator anymore. It's all happening together in the material.
You got it.
And that nonlinear time-like feedback, connecting that back to the big picture, how does embedding that kind of self-regulation push us closer to robots that are genuinely autonomous and adaptable? Robots that can, learn more organically from just interacting with the world.
Oh, it's a massive step because it allows for inherent natural seeming movements like a walking gait or maybe swimming motions without needing that constant top-down control signal for every tiny adjustment. It means the system can inherently adapt its rhythm or movement based on the feedback it's getting through its own physical state.
Less programming, more emergent behavior.
Exactly. It integrates sensing, control, actuation right into the physical structure. It's a pathway towards machines that don't just react based on code, but can adapt, maybe even decide, and act much more autonomously, learning as they go through physical experience. So, okay, what does all this mean for the future? For that quest for AGI, artificial general intelligence. Soft robotics is still pretty new, but the implications are huge. The takeaway seems to be that to get from today's AI to real AGI, machines might actually need these soft, adaptable bodies. Think about how we learn, how most life learns, really. By moving, touching things, trying stuff, failing, adjusting. That's how we navigate this incredibly complex, messy world.
Something current AIs stuck in the digital realm really struggle with.
Exactly. And it's not just about, say, a robot being better at picking things up. It's about a deeper kind of understanding. To truly know what an apple is, well, we don't just read a definition. We've held one right and tasted it, maybe dropped it, seen it bruise, cut it open, felt its texture, maybe even watched one rot.
That's all tacit knowledge,
Right.
sensory, contextual.
Right. It's knowledge that current LLMs, no matter how good they are with words, just don't have.
Yeah.
They process descriptions of apples, not the apple itself. So having that direct physical connection, that feedback loop with the real world, it potentially gets around the limits of language that today's AI faces. It could allow an embodied AI to build a completely different understanding of the world, a conception from its own point of view, based on its own experiences.
Especially if it had different sensors than us, right? Like infrared vision or smelling diseases, like the article mentioned.
Imagine that. It could develop a perspective, an understanding of reality that's entirely non-human, but potentially incredibly useful. Julius Andini, he's a professor of bioengineering in Genoa, he said, if you want to develop something like human intelligence in a machine, the machine has to be able to acquire its own experiences. You must let it learn from experience as children do. And that likely requires a body.
That really brings it home, which raises a pretty profound question, doesn't it? If real intelligence, or at least human-like intelligence, is so deeply rooted in having a body and interacting physically, what does that mean for us as we start designing machines that learn this way? What kind of truly unique understanding might an AI develop if its childhood involves sensing the world in ways we can't even imagine? And, well, how might that eventually change how we see the world ourselves?
A lot to think about there. So let's quickly sum up this deep dive. We started by looking at the maybe unexpected limitations emerging in even advanced disembodied AI, how they struggle with complexity and true reasoning. Then we explored this big shift in thinking towards embodied cognition, the idea that intelligence isn't just computation, but a unified process of acting, sensing, and thinking distributed through a physical form. And finally, we touched on the exciting potential of fields like soft robotics and autonomous physical intelligence API, which are actually building smarter bodies, materials that can sense, control themselves, and learn through interaction.
Suggesting the path to AGI might not just be bigger brains, but better bodies, too.
Exactly. It suggests the road to truly intelligent machines might need to be built, quite literally, from the ground up, with flexible, adaptable sensing materials. We hope this deep dive got you thinking about this incredible intersection of AI, robotics, and what intelligence even means. What might a truly intelligent future, born from embodied experience, actually look like? We're definitely excited to keep exploring that with you.